Okay, so the second part, we look at what we call enhanced entity relationship modeling. So it's some extensions to the entity relationship model that we have seen to deal with more complex objects. And the reading for that is chapter 13. Okay? So what is enhanced entity relationship model? Well, there are a number of areas where the objects have got more and more complex. So for example, things like geographical information system, computer-aided design, computer-aided manufacturing. These are areas that generate very complex scenarios, because for example, if you're working in CAD, you might have parts that relate to other parts or relate to other parts. So there's a lot of complexity in the real world that you're trying to model. And for those, sometimes what you are offered by the ER model is not enough to represent the complexity of the real world. So because of that, they came up with enhanced entity relationship modeling, which gives you further constructs to give you more wealth of semantic information to represent real-world complex objects. And in particular, what we're talking about is a specialization and generalization, which is the more important one, and then aggregation, which has a specific form also called composition. So those are the main things that you have to understand as part of this enhanced entity relationship modeling. And the idea is that if I have something like that, I have a statement of requirements and I have a staff. And my staff, I have different types of staff. So I have managers who get bonuses. We know all about this with the banks these days. So we have the bonus of the managers. The salespeople, they don't get bonus, poor people, but they do get a sales area, a car allowance, so they have their own things that they get. And secretaries, maybe they don't have a bonus, they don't have a car, but they have things like typing speed and other things. So they are members of the staff, and they have some things that are common to all of them, but they all also have their individual things. So if you represent that in the database as it is, we have a member of the staff, and I have the name, the job title, the bonus. I'm going to have a lot of blank data, sparse data, because only the managers have bonus. Then I have the sales area, again a lot of sparse data, because only some people are going to have the sales area. Same for a car allowance, and same for typing speed. So it's not particularly good design, because I'm ended up with a lot of null values in my data, sparse data. So these concepts of generalization and specialization are going to help me to improve on situations like that. So what I have there is that, and if you've done Java programming, object-oriented programming, you should be able to identify these things, because this is all to do with class hierarchies, attribute inheritance, and so on. So you should be familiar with all of this. Most of you probably have done some form of programming, so this should not be completely new to you. The idea here is that entities might be in a hierarchy. So we have super entities and sub-entities, superclasses and subclasses, whatever you want to call them. And the idea of a superclass or super entity is that you have an entity that includes distinct subclasses that we need to represent in the data model. So in this case, for example, we have the staff entity. That is the super entity. But within that, we have subclasses like the manager, the sales representative, and the secretary. There are subclasses of the superclass staff. And what we have is that what we're representing there is a hierarchy. A manager is a type of staff. A secretary is a type of staff, and so on. And they are in one-to-one relationships. A manager is a member of a staff. Every staff is identified with one manager. So it's a one-to-one relationship between those. And then we have this idea of attribute inheritance. All of the attributes of the superclass, the staff, also can be inherited by the subclasses. But the subclasses define their own data as well, define their own attributes. So the staff has some commonality, such as the name, the address, etc., that is going to be inherited by all the typists, the sales representatives, the managers. But then each of them are going to define also their own attributes, which make them specific. So we arrived at that by a process of either generalization or a specialization. They are working the opposite way but reach the same conclusion. So if we think about generalization, what we're trying to do is minimize the difference between entities by identifying the common features. So I look at that and I think all of the stuff have a common feature, which is the name, a common feature, which is the surname, common feature, which is the address. So all of that is the generalization. I look at what I can identify, which is general to all. A specialization is the opposite. I look at the general stuff and I think, how do I actually differentiate between them? Well, the managers have a bonus, the typists have a typing speed, and the sales representative have car allowance and whatever. So I'm specializing. So they are arrive at the same conclusion, but through the different means. And note also that this can become more complex, because we can have subclasses of subclasses, we can have shared subclasses, so we can do all sorts of fun things with this. So for example, a postgraduate student may be a subclass of taught students. So I have taught students, I have postgraduate taught students, I have research students, so I can specialize and generalize. And a postgraduate student might be also a kind of postgraduate student. So I have postgraduate taught, postgraduate, so I can have shared classes, I can make my my model more complex by using all these kind of like hierarchies of concepts. So how do we do that? Well, if we go for the bottom-up approach, we start by looking at what is different, and then we try to generalize. So we say, okay, this is the salesperson, this is the manager, and this is the secretary. But when I look at those that I've identified individually, I see there is a commonality. They all have a staff number, they all have a name, so let's generalize that. So there is a super entity called the staff, which has a name and a number, and then each of them define some sub-attributes, some attributes of the sub-entities. Okay? Or alternatively, I could do it with the other process. So I start having my generic entity, my entity that defines all of the different types of stuff, but I think, hold on a minute, in there I might have some of the staff that don't have a bonus, some of the staff that do have a bonus, some of the staff that have typing skill or not. So I identify the commonality, but also what is different. So I am doing the specialization. So either by generalization or specialization, I can arrive to this type of class hierarchy. What we have to look at additional to that is some constraints that we can have. And these are what we call disjoint or overlapping constraints and mandatory or optional constraints. Okay, so let's see how those work. So if I look at the disjoint constraint for a generalization or specialization, what I have is, what I try to describe is the relationship between the super entities and the sub-entities. So can a subclass be a member of more than one? Can a superclass have members in more than one subclass? So for example, if I tell you undergraduates and postgraduates, that is disjoint. You can either be an undergraduate or a postgraduate, but you cannot be both. So that is a disjoint constraint. I have sub-entities, but you can only belong to one or the other. So there is a disjoint constraint there. On the other hand, if I say the staff and the student, a member of the staff could be registered as a student, so there will be overlapping sub-entities, because I could be both a member of the staff and a student at the same time. So then it will be defined as a overlapping constraint. Okay? So I can either have overlapping or disjoint sub-entities. At the same time, I can have mandatory or optional participation, and that means that every member of the superclass must participate as a member of at least one subclass. So for example, if I say a staff member must be identified as either a manager or a counsel or a secretary, that is mandatory. But if I say a member of staff may not belong to any of those classes, then that is optional. So I could have a member of staff which is something else, an administrative person who is not defined as one of those. Then that becomes optional. So mandatory is where each entity has to belong to one of the, each entity occurrences has to belong to one of the sub-entities. Optional is where you might belong to the super entity, but not necessarily to one of the sub-entities. Do we understand that? Yes? So disjoint versus overlapping, we understand that? And optional versus mandatory, do we understand that? Yes? You look like you do. I don't know if you do, but you look convinced. All right. So representing it in UML diagrammatically, UML gives you its own kind of like notation for this specialization and generalization, which is this kind of like arrow. So this is the notation in UML. We have a branch and a staff, and they are identified there as having a branch has a staff, and it's a one-to-many relationship. A branch has many staff. Each staff belongs to one branch. Now, we know that a staff is a superclass, because this is what this arrow is telling us, and it's made out of 3 subclasses or 3 sub-entities: the manager, the salesperson, and the secretary. And because this is defined as this type of specialization, generalization, it already assumes that these are going to inherit the attributes of the superclass into the subclasses, but then they define their own attributes. So these are the subclasses. And this is how we put our optionality and mandatory and disjoint and overlapping constraints. So either here we put optional or mandatory, and that is for the participation to constraint, and then we put and or for the disjoint constraint. So if we're saying this is optional, we're saying that a staff member may not be either a manager or a salesperson or a secretary. He could just be a staff, but without belonging to any of the sub-entities. On the other hand, we say that this is a disjoint constraint is and, so we have that a staff member could be a manager and something else. If we have or, then it should be one or the other, okay? But and means there is an overlapping constraint. We could be more than one. So we could be a manager and a secretary, a sales and a manager. So if we do that in the cross-foot notation, Visio offers you this representation for it. So this is a category symbol to specify that there is a subclass. There is no particular way of entering this, but you can enter text in the diagram. So you can enter a text box to identify your disjoint or overlapping, mandatory or optional constraints. And what this will do is it will automatically put your primary key from the parent entity into the sub-entity. So you will automatically have the manager and the secretary and the salesperson all inherit the staff number as the key from the parent entity. So they are linked like that. And then, of course, note that any of the sub-entities can participate in relationships independently of the super-entity. So they can join their own. So, for example, a manager might have a relationship with a branch. So I can have that a manager manages 0 or 1 branches, and each branch is managed by one manager. Okay, so I can have then each sub-entity, if I want, identify in particular relationships with the rest of the diagram. Are we all happy with that? Yes. Another way to do this, which at the end of the day is how things are going to be implemented, is to define one-to-one relationships between the super entity and the sub-entities. So if you had any software that didn't allow you to specify the categories or the kind of UML symbol for specialization and normalization, what you are really represented at the end is a one-to-one relationship between the parent entity and the child entity. So you can do it like this. You could have a staff is a salesperson, so it's a one-to-one. A staff may or may not be a salesperson, so it's optional. But every salesperson must be a member of a staff, so that's mandatory. Equally, I can have a staff may or may not be a secretary, but each secretary is going to be a member of a staff, so that is going to be a one-to-one, optional at one end, mandatory at the other. And the same for a manager. And in the same way, if I do it like this, I can have relationships between the sub-entities and the super-entities, and I will have the key of the parent entity will become the primary key for this, and the foreign key to link to the staff entity. Okay, so that will link both tables, both entities, and tables eventually when we implement that as a relational model. So are we all happy with that as well? So we can always represent it in this simple way, one-to-one relationships. So another example of something like that is that we might have a person, if we use the UML notation, and a person might be a staff, a private owner, or a client. Now in that case, every person is going to have a number, which is going to be the identifier, and a name. But if they're a staff, they might have also a position and a salary. If they have a private owner, they might have an address and a telephone number. If they're a client, they might only have a telephone number. Now, that we say is mandatory or, so that means that a person must either be a staff, a private owner, or a client, one of the three. And we say or, so they are distinct categories, it's disjoint. So it either is a staff, or a private owner, or a client, but it cannot fall into more than one subcategory. Okay? And then I said, a staff, I define then a hierarchy of that, which is a supervisor and a manager. The supervisor may or may not have his own attributes, the manager might have a start date and a bonus. And they're going to inherit all of the attributes of the person and all of the attributes of the staff by being a subclass of staff. Okay? And here I'm saying they're optional and disjoint, so I'm saying a staff could neither be a supervisor or a manager. They could be none of them. They could just be identified as a staff but not belong to any of the sub-entities. But if they belong to one of the sub-entities, it is either a supervisor or a manager, but not both. Okay? So then we come to the final concept of aggregation. Now, aggregation is kind of less important because you're going to find very few times where you actually have to use that. If you haven't signed it, make sure that you do before you go. So even with a specialization and generalization, you shouldn't try to curl the curl, as we say in Spain. You don't have to overcomplicate things. If a diagram doesn't ask for it, you don't have to try to put it in. Okay? So if you can model things without using EER, that is fine. You don't have to use it. Because at the end of the day, these extra concepts are there for when you are trying to model very difficult, complex objects. So your general modeling scenario may not need the use of a specialization or generalization. On the other hand, if you do see that you can use it and it makes sense, then do. This is more so with aggregation. Aggregation, while normally doesn't really have a place in a diagram for a normal kind of like set of objects. They might only come as a need to use it when you are modeling quite complex objects that require it. So don't try to overcomplicate your diagrams using all sorts of like complex aggregation and specialization and generalization if you don't see a need for it. If I ask you what are the concepts within enhanced entity relationship modeling, then you should know what they are. And if I say in this diagram try to use it, then you should try, because I might say that in an exam. But that is to test whether you understand the concepts or not. It doesn't mean that in every real world scenario you're going to have to use these. Okay? So you have to kind of like understand them but not necessarily enforce them upon the diagram if they don't fit in there. So when we have aggregation, we have seen generalization and specialization already, and this is just kind of a special type of it, where instead of a is a hierarchy, we are modeling a part of hierarchy. So we have here a whole, which is made out of parts, and they all kind of make up the whole. So for example, if I have something like a software product, with a product number and a name and a price, I might have that is made up of a program and a manual. So there is the whole, which is the whole software product, and it's made up of parts. One part to the software is the program, the other one is the manual. So it's a whole thing made up of parts. We could equally possibly model this with a specialization and generalization, but we might say this is aggregation. In the old notation, in chain notation, you could use something like this, where there is an A to indicate what you're modeling is aggregation. This does not exist in Crowsfoot notation, and I haven't seen it in UML either. So you might not be able to specify that you're trying to do aggregation unless you put a text note to say this is aggregation. At the end of the day, you can start implemented in a similar way, but you might conceptually want to identify that what you're trying to do is aggregation. And the book mentions composition, which is a special form of aggregation. And this is where you have an association between entities, but there is a strong ownership and coincidental lifetime between the whole and the part, which might not always be the case for aggregation. So if we think about a newspaper, which is made up of artworks, that is, the whole is the newspaper and the artworks are the parts, but they are going to exist in coincidence with one another. The parts, the kind of like the newspaper has some kind of like responsibility for the artworks in terms of the creating the objects, destroying the objects, amending the objects. So there is some kind of like coincidence in the lifetime between the parts and the main object. Okay, so in that case we're talking about composition. It doesn't matter so much that you identify composition exactly, because at the end of the day, again, unless you're dealing in very specific scenarios, it isn't going to make a difference to you. But that is kind of like the difference between aggregation and composition. And as I say, you only really need to think about them when you really need to model the is a part of relationship instead of a more generic specialization and generalization relationship. And where there is things like implications of the creation, deletion, and update of the things that are closely related. So for the newspaper, the artworks may be closely related in terms of how you manage them, create them, update them, delete them. So you might want to, in that case, use aggregation. Because there's no clear way of modeling this in UML or in the Crowsfoot notation, again, you'll model it with the one-to-one relationships that I showed you in the second Crowsfoot notation diagram. So you'll just model them as a one-to-one or maybe one-to-many, but using normal relationships in the diagram. So how do we build this EER model? So we identify, as we did, so essentially we start by building an ER model. So we look at the grammatical analysis. Any nouns that we identify, we think of them as being either attributes or entities. Any verbs that we identify, we look at them as being possibly relationships between the data. We look at the cardinality constraints, we look at the participation constraints, and we begin to create our model. We look at candidate and primary keys. And then we might decide to look at whether there is any chance of specializing or generalizing to create these class hierarchies. So we start with an ER model, and then we see whether we can actually fit in EER in a manner that makes sense. So if we do, also we look at aggregation. Is there any way that we could model aggregation in there, in our thing that we're trying to model? We draw the EER diagram. There might be that we're working with a number of designers, so we might merge the different designs that are coming from different angles. We might be trying to model each user group differently and merging together the views. So sometimes we design the whole system, sometimes we design every different external view, and then we try to put them together into an overall design. So that's what they call view integration. Once we've done all of that, we need to modify. We need to create our logical design. So we've done our conceptual design. So we need to think about how do we convert this into the relational model, which is our model of choice. So we need some rules for that. If we have entities, they convert straight into a relation in the relational model. So that is quite straightforward. Any entity in my ER diagram becomes a relation in the relational model. If they are strong entities with simple attributes, they become a table. If they are weak entities with simple attributes, they become a table, but the primary key of the owning entity will form part of the child entity. So for example, if I have the work, employee, and the dependent will have the employee primary key as part of that record. If I have binary relationships, and they are one-to-many, the foreign key will go onto the many side of the relation. And the software will automatically do that for you. It will automatically put the primary key, the foreign key, in the right side of the relationship. If I have one-to-one relations, and they are both mandatory, I can combine them into one table. So for example, if I have one table for the school and one table for the dean, I don't have to store them as separate tables. I could put all of the details of the dean, because there's only one, in the school table. Okay? If they are one-to-one with optionality, then they stay separate, but I put the foreign key in the mandatory side of the relationship. And if they are many-to-many, I need to break them down. So I cannot model that into a relational model. I find an intersecting entity, and that intersecting entity takes the primary key for both entities that are forming that many-to-many relationship. If I have complex relationships, the ternary or quaternary relationships that I saw at the beginning, again I have to break those down into the intersecting tables with the primary keys for each intersecting table appearing in there. So for example, with the tertiary key there that I had, which was a client, a branch, and something else, I have to end up with a table that has the client number, the staff number, and the branch number. So it will be, again, breaking down with an intersection entity, which takes the primary keys of all of those particular entities. If I have attributes, if they are composite, then I am going to break down and store the constituent values. So if I have address, I am going to store the different parts of the address instead of the composite attribute. If I have multi-valued attributes, for example, how many sports a particular person played. Remember that in the relational model we cannot have more than one repetition of values in one intersection of a row and a column. So I have to deal with that. So I create a table for the sports played, in this case, for example, with the primary key of the student being associated with the sport played. So I can identify which student plays what sport, but it becomes a table. If I have superclasses and subclasses, then one table for the superclass, one table for each subclass, and the superclass primary key goes to the subclass, so that we can link them together as a foreign key and as the primary key. And again, if I have aggregation, I end up with one table for the product, one for each of the components, with the product primary key being part of the component, linking both tables together. So I think we ran out of time.